and we are welcoming Myles Cupp. He's from Colorado State University. We are looking forward to his presentation. Virtual reality as a value engineering method in machine shop learning.
All right, so let's go ahead and get started. So let's talk about our agenda. We're going to introduce the topic. We're going to discuss some observations that I've made in my career, and then we're going to sort of step through the paper, talk about value engineering, educational systems that have value engineering methods applied to them, virtual reality as a mechanism of applying a value engineered analysis, and how to quantify how you can increase the value of an educational system with value engineering using virtual reality. I'd like to introduce myself just really quick. These are some of my credentials. I'm an electrical engineer by trade, getting my systems engineering PhD. I've done a lot both in education and in industry. My day job is I work at Disneyland, so a lot of the work that I do involves theme park attractions and things like that, where I have to compel stakeholders who don't understand the engineering side of things by convincing them of how value is added by doing something that doesn't on paper make you any money. Right? Because when you make a theme park attraction, you're adding a lot of really pretty stuff. How does that drive value? It's just cost. So you have to use value engineering, and I'll explain what those methods are. What I've discovered during my time working in industry is I didn't have any sort of on-hand jobs training. I went to school, came out of school, went right into industry. OSHA reports that 34% of workplace injuries occur in the first year on the job. What I discovered is that you need experience to have intuition about how to be safe on a job site, but you have to be exposed to those hazards in order to get that experience. So you need experience to be safe, but you need to be safe to get experience. How do you do that? So this is an example of a traditional machine shop environment where you have the instructor and you have the student standing off to the side, and the instructor is saying, okay kid, here's how you use the lathe, right? At what point does that student who has never had the hands-on experience with that lathe start using that lathe? Which is very dangerous. You know, a lathe can rip your arm off in a second, right? I don't mean to be, graphic, but that's the level of safety we're talking about. And I found this on construction sites and in education, and that's sort of where my brain went when I started to delve into my PhD. So, to be safe on a job site requires you to have exposure to this, but also specialized training. And that specialized training is a bottleneck, because in order to get through that program, you need the supervised instruction from somebody with experience. Not only do you need supervised instruction, but you need the equipment altogether, right? You need to have a lathe. A lathe costs tens of thousands of dollars. Value is lost when a lathe is not turning parts, but is just being used to educate somebody. Okay? And you also have student anxiety, right? People who are just scared of being exposed to the hazard, as they rightly would be. A lathe can be very dangerous, or being on a construction site can be very dangerous. So what we need is to address this in a quantifiable and systemic way, and that's where systems engineering is going to help you. So let's talk real quick about what systems engineering is. I'll give the definition up there. The goal is to manage risk in systems engineering. Identify what does the customer need. What is the risk of a late delivery of that need? What are the risks of costs, risks of negative unintended consequences? And conversely, we then have to measure what is the acceptance if we don't do a systems engineering approach? What are the risks if we don't do this analysis? That's what systems engineering is all about. It's the management and reduction of risk. So since it's a way to manage risk, we have to ask the question, is there a way that we can give users an experience with hazards without exposure to those hazards? The obvious answer, of course, since we're all at a VR conference, is virtual reality. It's one way that we can do that. But can we do that without significantly increasing the operational expenditures? Can you convince somebody who's not an engineer of the value of doing this approach? That's what a value engineering method is. So let's talk about the definition of the value engineering. Its definition is that it's a structured approach to improving the value of a product, system, or service by balancing its functions with the costs required to achieve them. It's simply a ratio. And there are a couple of ways you can look at that ratio. All of these are valid. That the value of a system is its function divided by its cost. Function divided by cost, and you can expand on that by saying it's function plus performance over costs, or capabilities over the project cost as a whole. So what does that mean? Let's define some of those terms. A function is a verb plus a noun, something that does a something else. So a function that I could describe for you would be a coffee machine. What does a coffee machine do? Brews coffee, verb, noun, right? But I can also describe the performance of your coffee machine. You can have a coffee machine that just brews 1 cup of coffee at a time and takes half an hour to do it. Or I can have a coffee machine that brews 10 cups of coffee at a time in multiple flavors in 60 seconds, right? So the assessment of value is inherently subjective. What do you need to achieve in your application? And that is going to drive your cost, because obviously to make that 1 cup kind of coffee maker is going to be more costly than making the super duper really cool coffee maker. So the goal of the value engineering is to enhance the value by optimizing what your functional performance requirements are while minimizing the resources that you need in order to achieve it. This leads then to a misconception that people have about value engineering. People, you might have heard it said, we value engineered away the entire system. Now it doesn't even do anything in order to save costs, right? In order to cut costs, right? People think value engineering means cut costs at all costs. That's not what it's about. Value engineering is about the maximization of the value of the system. So when you do that, you then change your perspective about what your system is going to do for you. What is your system going to achieve when you increase functional performance versus its costs? So in the case of a machine shop lab, and these are photos from the Colorado State University Engineering Manufacturing Educational Lab, what they need is they need a method to service an ever-increasing number of students who need exposure to hazardous equipment without increasing the risk to themselves or to the program. What do I mean by risk to the program? In a program of education, their verb and nouns formulation is that you need to transfer knowledge. You have to teach students to some minimum level of competency, and you have to do it within a certain time frame. If I had 10 years with one student, I could educate a lot of information into them. But if I have a classroom full of 30 students and I have 3 months to make them competent enough to use a lathe without instructor supervision, that is what my performance requirements are. So our function is to transfer knowledge, and our performance requirements are throughput, time, and minimum competency. But the issue is that with rising student populations and an industry that is increasingly demanding more from students, competency with high precision machines, dangerous machines, construction, there is a constraint that's happening right now across many universities where they cannot educate the number of students that are coming into their programs. They're reaching a capacity. Not only that, there's also a capacity constraint on the number of instructors that you can hire. There's significant overhead to hiring an instructor, training an instructor in all of these traditional methods, and somehow keep everybody safe, right? That's the other major constraint that's driving this. So this is just a simple chart showing the projection of student enrollment at the Colorado State University's EMEC lab, where they're at a flat capacity, but their student enrollment, that projection is blowing the roof off of the lab. How are you going to keep up with this demand? Because over time, you're going to be losing value of your educational system, that there's a body of students that requires education and you're not able to service them. So I've already discussed a little bit about the limitations of traditional educational methods to increase capacity. You have to spend a lot of money to buy new equipment. You need space for that new equipment. There's constraints on how much that space costs. Talking to the chairman of the department there, to expand the lab is $2 million. $2 million to expand the lab, train and hire new faculty, and once you've done that lab expansion, that's it. You're at your maximum footprint now. You can't go any further. So there's going to be a maximum capacity increase that you can have with a traditional method. So we need to analyze this problem. How do we increase capacity to keep up with this demand without spending millions and millions of dollars? So what we're proposing in this paper is a value engineered educational system where our function is the student throughput, that's our value, and then the function is the capacity of students that you can get through the program. assuming the minimum competency levels. That's why I don't have a term for performance in here. I'm assuming we're going to pass all these students through and they're going to be great. Okay? Then we're dividing that by our costs. What are all of the costs driven into this? I won't go through every single term here, but you can see development, maintenance, space, equipment, and so on. So how can we use now a technology towards our value engineered educational system? So value engineering includes using novel technologies to increase the value of your system. And virtual reality is one such technology that's ideally suited for that integration into the traditional workflow. Now, of course, the advantage is that you heard them in the previous talk if you were here for it. You can customize those experiences. You can make them repeatable. You can flat rate spatially expand the educational program. Because for a virtual reality system, all I need is maybe an 8x8 square foot of space, a computer, and a VR headset. And I can expand that linearly or exponentially, right, depending on how you structure your educational environment. And inside of that environment, you can also assess the performance of students as they go through your virtual reality program. So it is in alignment with a value engineering approach to use VR to supplement the traditional educational method. By doing that, we can increase the value because you can now increase the capacity of your educational program. Coming back to what I said a second ago, cost reductions in the misconceived way of thinking of value engineering can never increase your capacity. You can never increase the value of your system just by cutting costs. Eventually, you'll saturate the amount that you can cut costs, but you'll never increase the capacity of your system. All of this leading us up to how do you then convince a program to adopt virtual reality to solving this issue? So here's one compelling way to look at it. This is if you take a value engineered system, but you don't use virtual reality. You use traditional expansion methods. I'll explain this chart so you understand what's going on here. The difference between the capacity and your costs, that ratio, that's what we're calling our value. The further to the left on here, as we look at the academic years, when you're not yet exceeding your capacity, there's a net gain in value there. That you can expand, spend a little bit more money, and you'll still increase your value. Eventually, you have to spend exorbitant amounts of money in order to get minimal gains in capacity. That's a net loss in the value engineering function. Where those two lines cross is where you start to get losses. But if I use virtual reality and I say I can increase the capacity of your program by supplementing with virtual reality, what then do I get? Well, you can see that if you increase the capacity with virtual reality, there's a greater amount of net gain as you move to the right in time over academic semesters. Hopefully everybody can see that that's a bigger gap there. That's more value in your educational system, all right? So we can analyze it that way and then show this is the potential value gain that you get. But you need to quantify that. That's all well and good, but how much gain can we get? Because in value engineering, it's the definition of the value is still subjective. How much are you willing to spend versus function and performance? So we need a way to convince somebody quantifiably with a number, this is what your program can get you and this is the way you can do it. So this is where we're now going to introduce another equation that's called the transfer effectiveness ratio. This is not an original equation. This actually comes from aerospace and military technologies back in the 50s, 60s, and 70s. When the military was introducing new training programs for aircraft pilots, they used flight simulators. They wanted a way to quantify how much time does a pilot spend on a simulator that they don't have to spend in the cockpit of an aircraft. And you can see there's different costs associated with those two systems. So it's a simple ratio where Y sub C is the time spent or number of trials to train an individual in the traditional method, and Y sub X is the time spent or number of trials to train someone who's already been trained in the simulator. So when you use that equation, and a value of 0.5 means that if you use the simulator, however long it takes in the simulator, you reduce the amount of instruction time in person by half. That can be huge. If I can say I can reduce the number of students that you have to train traditionally by using virtual reality, and I can double the throughput of your program, that's a compelling argument to make. So it is possible then to prove the utility of a VR system when you apply it to an educational environment by calculating the TER for an experimental versus a control group. So here's the proposal of our method that we're going to implement. This is Still theory, but here's how we can apply it. That you can demonstrate the efficacy of this by taking a simple experiment. Create a virtual environment, model to the most bottleneck piece of equipment in a lab, in this case a lathe, because there's only 3 of them in this particular lab. Develop a digital twin of that, create a guided instructional curriculum for using that lathe, deploy them in an academic semester, collect data of the performance of the people who underwent the VR training versus those who didn't. Very typical method, we saw it in the last talk, right? Makes sense. And calculate the TER to determine if appreciable knowledge transfer was obtained. So this is a sample of the digital twin that we've obtained for using. This was actually an open source lathe model. That's the same as what is used in the lab, which is kind of cool. So you can take that digital twin, bring it into Blender, bring it into Unity, model interactions with that lathe to train the students about how to interact with this piece of equipment. How do you turn it on, right? You don't know just from looking at it. You might need some practice. So here are some sample calculations that point towards the right kind of application. Approximately 189 students per semester require 2,000 machine hours. Most of that time is not spent turning parts, it's spent time standing in front of the machine. And that's the maximum amount of students that the lab can currently support. If 2 hours of in-person training can be offset by supplemental VR training, I put a student in VR, train them to competency, put them in front of the machine and save 2 hours, that's going to equivalent to be about 21% increase in student throughput per semester. That's a pretty significant gain. Now it's going to be up to the stakeholders to decide, is a 21% increase in throughput worth the investment in VR? That even a modest reduction in physical lab space without sacrificing competency can lead to those substantial gains. And you don't have to deploy it necessarily on campus. You can have students take a VR system home and practice on a lathe in their own home. And as mentioned in the last little bit, there's challenges to the adoption of VR in the current space. I think there's a lot of opportunity for using AI to help with the development and customizability of these systems going forward, and that's something that we want to research as we deploy this. So in conclusion, the definitions of systems engineering and value engineering were hopefully described clearly enough, dispelled some misconceptions about value engineering, and proposed a method for calculating a TER so you can take your own VR system, calculate a TER, and then use that to prove to non-engineering stakeholders why a value engineered virtual reality system is the way to go. So thank you very much for your attention. Hopefully there's time for a question.
Great.